Hi, I'm going to talk a little bit about a three-phase alternator that uses two stators. Dual stator alternator. Okay, why would I want to use two stators? Well, obviously for more output. But there's another reason. If we look at the old version, okay, my old version was a radial arrangement, which is very good mechanically. But what happens there is that you have a limitation with a single stator, where your output is about a maximum of 600 to 700 milliamps, and beyond that, even if you increase the rotational speed, the inductive reactance which is generated in the coils causes a self-limiting effect. So I figured that with two stators connected in parallel, like this, if you have the rotor in between, a disc-shaped rotor in between, with the magnetic flux being accessed on either side simultaneously, then stator 1 receives the flux from one side of the magnets, the stator 2 receives the flux from the other side of the magnets. They each have a separate diode bridge to produce DC, and both stators generate about 600 milliamps of charging current, and if you combine them in parallel, your output is then 1200 milliamps of charging current, which goes through the load. So even though the load receives 1200 milliamps of charging current, neither stator is conducting any more than 600 milliamps. So the self-limiting inductive reactance problem of the coils is not exceeded in either stator, but you're still getting a greater charging current output. That's the plan. I didn't know if it would work because of a number of possibilities of problems. In particular, I wondered if there would be negative interactions in the pulses of the coils on opposite sides of the stator. In other words, would the AC sine wave in one phase on one side interfere with the sine wave on the coils on the other side? Apparently not, at least in this arrangement, because it does work. Give you a closer look here. The rotor, as I said, is disc-shaped, and the magnets, there are 6 magnets. So you can access the magnetic flux on either side of the rotating rotor. The magnets are like this, a stack of 6 neodymiums, disc-shaped neodymium, to produce a cylinder. The ones I got were this brand. They cost about $8 for a 3-pack at Princess Auto. So, those are your magnet packs, 6 of them. The coils on either side are arranged in three-phase arrangement, 9 coils for each stator. The coils on one side are slightly smaller than the ones on the other side because they were designed for a different setup. These ones were designed to access these large magnets here on a large wheel. These ones were designed to fit tightly around this housing in this design. So they had to be a smaller diameter coil. But they both have about the same output. Now, talk about the idea of different types of shape of rotor. Now the disc-shaped rotor is like this versus the cylindrical rotor, which was like this. Okay, cylindrical rotor, you can see the magnets extend around the periphery of the rotor. In the disc, you can access the magnets from either side of the disc. You can see I've removed the magnets from the old cylinder to place them in the new disc. Making the drive shaft for this thing isn't that easy. You have to make sure that it's running true. So what I did was I used large washers and spacers and large nuts on a 5/8 inch threaded rod, using idler pulleys at either end to support it. The difficulty with a large disc like this is that as it rotates, because it's a big disc, you're having magnetic pull at the periphery and dragging it side to side as the disc rotates and the magnets come into contact with the metallic cores of the coils. So this causes dragging forces on the disc as it goes around, which creates a wobble. Now, this is the problem with the disc-shaped rotor, as opposed to the cylindrical rotor. In the cylindrical rotor, it's mechanically better because the pull is in line with the rotation of the disc, so it doesn't tend to create wobble. Whereas in the flat disc rotor, in our current arrangement, we do get a wobble pull. Okay, you can see that when I there's a wobble there as the disc rotates. The reason why the wobble is the problem is because you need to reduce the gap on either side of the rotor. The gap between the rotor and the stator cores should be as narrow as possible, but because there's a wobble, it limits our ability to bring the two stators close to the disc. So right now there's a little less than 1/4 of an inch on either side. It would be nice if it could be a little bit closer, but it has to be kept clear. It has to rotate freely without any binding against the polypropylene disc boards. The disc boards are like this. 9 holes arranged in a staggered arrangement. Okay. This is board 1 with 1 3/8 inch holes to accommodate the larger coils. Board 2 with 1 inch holes to accommodate the smaller coils. with a 1.5 inch hole in the center to clear the drive shaft in either case. And note that the holes are in staggered arrangement. Okay. That means that instead of having the coils aligned on directly opposite sides of the disc, they're aligned out of phase, or separated by 20 degrees. Each of the 9 coils is separated by 40 degrees around the circle, so 20 degrees offset on the other side means that these ones are in between these coils. What this does is it limits the jerkiness of the magnetic drag. If you had them aligned, then the magnets would attract on both sides at the same time, then to the next set, then to the next set, producing a very strong drag point and a jerky rotation. By separating them out, you get a smoother rotation. Okay. The mechanical issues of attaching the coils to the boards are a little bit difficult. I had to find some way to connect these coils so that they would be secure, but at the same time I couldn't put any connectors or straps on this side because you can't have anything to interfere with the gap. So on this side I was able to get away with just using epoxy because they're a lighter coil. On this side I didn't want to rely entirely on epoxy, and so I developed this strap system where you can see they're connected with little hooks, and then the plastic zip ties are wrapped around the coils in this manner. So that you get a system like that. Now that alone causes kind of a warping of this large board, because the tension on these straps tends to bend it backwards, creating a bow in the center, which causes a binding of the rotor. To get around that, I put a second ring at the back of the coils to prevent them from pinching together. Kept them all straight, kept the front flush. Again, you have to keep things flush here. Mechanically, it's a more difficult system than the radial because it's more difficult to construct. You have to do it in pieces because you can't just drop the stators on top of the shaft. They have to go through the center hole, which means that you have to do it in parts. The spacing rods have to be put in the proper order. If you have any experience with auto mechanics, you should be able to handle it, but it's more difficult and less durable, I think, than the radial type. But I wanted to know basically proof of principle, and the advantage of using a disc-shaped rotor, as I said, is that you can access the magnetic flux from both sides of the magnets simultaneously. If you use a radial rotor, radial arrangement, you can only access the magnetic flux from one side of the magnet pack because the other side is buried in the disc and you're only accessing one side. If it's in a flat one like this, you can access both sides. buried into a disc, rotating radially, you can only access one end. Which means that if you wanted to do a double stator with the radial arrangement, which is mechanically superior, you'd have to double the number of magnets. You can do it, but it'll cost you a lot more. Your choice. I would like to build one of the radial ones, but it does require one set of magnets for each stator. Okay, I'm going to put this back on here so that you can take a look at what's going on here. Getting a glare there. I'm just going to crank this. I'm reading 40 volts there, but it's an easy 35. I'm still reading 38.7. But it's an easy 35 volts. Now, if I switch the meter to read current, okay. Up to 1.4. That was 1.35 amperes, which is 1,350 milliamps, as opposed to the self-limiting 600 milliamps that we were getting from a single stator. So yes, it works. You can see that stator 1 and stator 2 each have their own 6-diode bridge producing DC output. You have alternating current in each of the 3 contributors to the bridge, and the output is DC. Each half produces about 600 milliamps. The total is up to 1.4 amps. So you take the output from either side, one side or the other, it doesn't matter. If I connect up a I'm going to disconnect the meter and just connect a load. That you could see that. Okay. And one more thing here. Just give you a look at the cranking handle I've used, where I've used a bearing on the end of the handle, which allows you to turn the handle, and the bearing turns in your hand. You don't have to let it slip through your hand. Okay, 2-stator, 3-phase alternator, 35 volts, 1300 milliamps.